Welcome back to lecture number 10 in our series on gravity and non-relativistic quantum mechanics. As a start, let me just recap what we did in the last couple of lectures. So we started with the cow experiment, and for the cow experiment, we were looking at the effect of a Newtonian potential, gravitational potential, and how it affects the phase of the wave function. So a wave function just in a homogeneous gravitational potential. Then we went one step further and we were asking how do we get this phase shift as a consequence of general relativity. And we looked at the Klein-Gordon equation or Klein-Gordon field in the semi-classical limit in the WKB approximation, where we take the limit where h bar goes to 0 and we get a phase, and then we calculate this phase in linearized gravity. So in gravity where we have the space-time metric expanded around a flat metric to linear order. So linearized gravity plus semi-classical limit of the Klein-Gordon equation. So with this we found that the cow phase, but we also found a more general effect. We found the phase also in the time space and space components. And those gave us, the space components gave us a gravitational decoherence effect that we discussed. And finally, in the last lecture, we were considering what happens if we have a superposition of clocks. And there we started with an Hamiltonian that we derived from the relativistic point particle Hamiltonian, with a relatively ad hoc replacement of the mass by mass plus internal energy. So today we want to try to tie all of this together a bit and bring it on a bit more solid ground. And we want to ask, in a way more general way, we want to ask if we have a Klein-Gordon field on a curved space-time and we take the non-relativistic limit of this, what is the Schrödinger equation that we get, so the non-relativistic Schrödinger equation that we get, and what are the relativistic, the post-Newtonian corrections to this Schrödinger equation. So the question today is, what are post-Newtonian corrections to the Schrödinger equation, corrections to, so first order, second order, and so on in 1 over c squared, to the Schrödinger equation on an arbitrary or freely given external background space-time. And let me say ahead before we start, if you look at the lecture notes, you will notice that they are very long. It's like 14 pages of notes, just because I try to be explicit and give you all the steps of the derivation. I put it in there in a lot of detail. And in this lecture, I will not give you all the equations. I will not go through all the details, but rather I will use this hour or hour and a half that we have in this lecture to point out the crucial steps to you, and so that hopefully with this information you can follow the lecture notes. And this is also your assignment for this week, so there is no other assignment, but your task is to read through those 14 pages of notes and not understand every single derivation and every single step necessarily. I mean, of course, it's nice if you understand everything, but try to get the essential points. Try to see what actually enters the derivation, and then what is done in order to get the result. So let me begin, and what we want to do is we want to look at the Klein-Gordon equation. I just write down the Klein-Gordon equation for you again. Okay, so this is the Klein-Gordon equation. The Lambert operator acting on phi equals m squared c squared divided by h bar squared phi. And we can think of, so as a first step, let me just we leave gravity out of the picture for now, and let me just give you the derivation, how we get the Schrödinger equation as the non-relativistic limit from this Klein-Gordon equation. Because this is exactly the procedure that we then want to follow one-to-one in a curved spacetime. So for now, we are considering flat spacetime. Let's first recap quickly where this equation comes from. So also how it relates to what we had in a previous lecture. So we found the Hamiltonian for the relativistic point particle, and we found that it's a square root expression. So if we try to canonically quantize it, we have this problem that we have this the square root of the momentum operator that we need to deal with. So what can be done with the Klein-Gordon equation is that we take the square of this energy, the square of this Hamiltonian. So and this would be, so h squared is m squared c to the fourth plus p squared c squared. Okay. And now we can basically quantize this equation by replacing these by the appropriate operators. So instead of h, we write the time evolution minus I h bar d by dt squared, and instead of the momentum, we write the momentum operator minus I h bar gradient squared, and all of this is acting on our field phi. All of this acts on our field phi, and now we can rewrite this simply as so if you just multiply, so if you take this square and then divide by h bar squared, then we find 0 equals the second order time derivative of our field minus c squared times the Laplacian of our field plus m squared c to the fourth divided by h bar squared phi. And if you divide this again by c squared, and you notice that the D'Alembert operator, is basically just the Laplace operator minus minus 1 over c squared, the second order time derivative. Then you will find this covariant form of the Klein-Gordon equation. But for our purpose, this explicit form of the Klein-Gordon equation is actually more useful, where we already have the separation of the different powers of c squared, because the spatial derivatives appear with a different power at a different order in c squared than the time derivatives, and this will prove important if we take the non-relativistic limit. So we can now look at this equation, of course, and try to take the limit where c goes to infinity. But if we do this with this equation, so we could just divide the whole equation by c to the fourth, then this gets c to the 1 over c squared. And this is 1 over c4. So if we take the limit where c goes to infinity, then this term vanishes and this term vanishes, and all we end up with is that our field phi equals 0. This is, of course, not the solution we are looking for, and the reason why we don't get any useful physical solution of this equation is that it turns out that if you compare the solutions of the Klein-Gordon equation to the Schrödinger equation solutions, they always have a fast oscillating phase that oscillates with the rest mass energy. We already encountered that a couple of times in this lecture. So there is a phase factor, and we need to extract this phase. We did this already in the lecture where we discussed the phase shift from general relativity. So we do the same thing here, and as an ansatz for our Klein-Gordon field, we assume that our phi of Tx has this fast oscillating phase that goes with I divided by epsilon, with a phase that generally could be a function of time and position. And then we have a power series, in our small parameter epsilon. So we have epsilon to the power n. It's a coefficient function psi n of t and x. Okay. So we will later see that the psi 0 function here actually is the Schrödinger equation wave function. That's why we call those coefficients already psi in foresight to that. And now, so our epsilon here, so our interest is the non-relativistic limit, where epsilon is 1 over c squared. So this is the small parameter that we're using to expand in. So far, before we already looked at the semi-classical limit. And this is the case where I use h bar as a small parameter, so where I use epsilon equals h bar as the small parameter that I use for the derivation. So once we have this psi, we can take the derivatives. So, for example, we can look at the time derivative of this function, and of course we just get the exponential out. And we can write, so if we take the derivative of the exponential, we get a factor I over epsilon out. So we get I over epsilon as dot. E to the I as divided by epsilon and this sum. And then we have the contribution where the derivative acts on our psi. So this gives us an e to the I as divided by epsilon, sum epsilon n, and then we have psi n dot. And now you see that here we have the 1 over epsilon. So this is of one order lower than this term, and what we can do in order to make them equal is we just write 1 over epsilon here and epsilon n plus 1 here without changing anything, and now we can just shift. The index here by 1. So instead of having our index, so n would normally run from 0 to infinity. So instead of having it run from 0 to infinity, we have it run from 1 to infinity. And we take n and n minus 1 here. So then it is still the same sum. And now, in a final step, what we can do is that we use a notation. This is just a matter of convention. So so our psi n's here, of course, always have n's larger than 1. And if we just by convention require that all coefficients with an index here that is smaller than 0 with a negative index are 0, so psi n is 0 if the index is smaller than 0, then we can go back and write this as a sum from 0. We just include this 0 here. So with this we can then write those two sums together in one sum. And if you look at the lecture notes, you will find this here in equation 10.7. You have the definition of psi dot, which then takes this form where we have I as dot psi n plus psi dot n minus 1. And in the same way, we can now do the same again and take the second order derivative, so we can get the second order time derivative and the Laplacian of our function phi, and end up with these equations 10.8 and 10.9. So this ansatz for our field phi we can now insert back into the Klein-Gordon equation, and then we get an equation that is then a power series in our small parameter. And so first, as an instructive example, so we are ultimately interested in the non-relativistic case, but let us first look at the semi-classical case where epsilon is h bar. And in this case, you have to, so in the Klein-Gordon equation, the time derivative and the spatial derivatives enter at the same order. So both of them, you can rewrite the Klein-Gordon equation, just multiplied with h bar squared, gives us h squared psi dot dot minus h bar squared c squared, the Laplacian of phi, plus m squared c fourth phi. And now we insert the power series for our field, and we obtain an equation like this. So if we insert the power series with epsilon equals h bar for the derivatives, so if we insert equations 10.8 and 10.9 into the Klein-Gordon equation, we end up with this expression 10.10. So we get this exponential in front, and we get a series, we get the summation of all the different orders of h bar, and then we get this longer expression here in the square brackets. That is now all the terms that are of the same order in h bar. And now we can go ahead and look at only this expression so the whole expression must be 0. That's the Klein-Gordon equation. So now we can look at this equation at any order. So we start at order n equals 0, and we put the whole thing to 0. So this means the square bracket term for n equals 0 needs to vanish. And you see, if you insert n equals 0 there, keeping in mind that all the psi n's vanish if n is smaller than 0, then the only terms you're left is that you get 0 equals so the m squared c fourth term, the constant term in the Klein-Gordon equation, is of lowest order in h bar, and from the derivatives you get the terms s dot squared, and you get minus c squared gradient of s squared. Or we can rewrite this, we can solve this for s dot and find that s dot is the square root of m squared c fourth minus c squared gradient at s squared. And what this is that this is just the Hamilton-Jacobi equation for a relativistic point particle. So S describes the action for a relativistic point particle, with the canonical momentum being the gradient of S in Hamilton-Jacobi theory. And this is essentially what we've used before. And now we can do the same. We can do the same for the for the non-relativistic limit. And for the non-relativistic limit, we insert now epsilon equals 1 over c squared. And we do the same, but now we have to pay attention to the fact that in the Klein-Gordon equation, the time derivative and the spatial derivatives enter at a different order in c squared. So we can divide the whole Klein-Gordon equation by c to the sixth. And then you get this first line expression, taking into account that the Laplacian term already has a c squared in front of it. And the reason why we need to divide by c to the sixth is because you saw in 10.8 and 10.9 that we get an epsilon squared in the denominator. So every time we take a derivative, we get an epsilon in the denominator. So if we take two derivatives, we get an epsilon squared. So if we take epsilon equals 1 over c squared, we get a factor of c to the power 4 in the derivatives. And this factor c to the power 4 we need to cancel. So that's why we need to make sure that this Laplacian term has a c to the 4 in the denominator. And then with this we can insert the derivatives expressed as a power series, and just as in the previous case, we end up with this series expression for our Klein-Gordon equation, which is now a different expression because it's now the expansion in c squared instead of in h bar. And then again, we can look at this at any order. So we take the non-relativistic limit, we put epsilon to 1 over c squared, and then at the lowest order, so then this was also the lowest order, so then at the lowest order n equals 0, we also get an equation for the gradient of s squared. Gradient of s squared acting on psi 0 equals 0 would be the expression that we have, or the gradient squared, or the gradient itself must be 0. So what we find is that our function s should be a function of time only, a function that does not depend on position. Now we don't have the time derivative in this equation at n equals 0 because it's a higher order term. Okay, so the lowest order tells us our phase in this non-relativistic limit is just a time-dependent. Phase. It does not depend on position. And now we can insert this into our equation. And if we do this, if you use that s is only a function of time, then all the spatial derivatives vanish, and then the term in the square brackets that must vanish at every order of n just reads 0 equals minus s dot squared psi n minus 1 plus 2i s dot psi dot n minus 2 plus I s dot psi n minus 2 plus psi dot n minus 3 minus the Laplacian psi n minus 2 plus m squared divided by h bar squared psi n minus 1. And now if we're interested at the next higher order, at the order n equals 1, then we can look at this and see, okay, n minus 1, this will give a psi 0 contribution. N minus 2 will not contribute because we get a negative index, which will be 0. So this one only contributes at the next order, n equals 2. This one will only contribute at n equals 2. This one will only contribute at n equals 3. This one will only contribute at n equals 2. And what we are left with is this equation for S dot. So it's this equation for S dot, which we can solve, and which gives us that S must actually be of the following form. S must be plus or minus, because we have an equation for S dot squared, plus or minus mt divided by h bar, plus constants in time. So we can ignore these constants, that will just be a constant phase, an overall phase of the wave function that will not be visible in any situation. And we have this time-dependent phase that will be with mt divided by h bar. You see here. mc squared t divided by h bar. Actually, in the end, if you include our epsilon, 1 over epsilon, that is still in the phase. So from this we get that our field is proportional to e to the minus I mc squared t divided by h bar. So plus minus here. Okay, and now we can further simplify this equation. We now know the form of S, so we can insert this. If we insert this, we get the following: we get 0. Then we get plus minus. So this cancels with this one now. That's just the equation at order n equals 1, leads to these two cancelling at any order. So what we are left with is this term. So this is now plus minus 2im divided by h bar. Psi dot n minus 2 plus second time derivative at n minus 3 minus this Laplacian term. And this is now the equation that we are left with, that we can solve now at order n equals 2, n equals 3, and so on. And if we look at the order n equals 2 and we solve this, then we find then we find again that this term still vanishes at this order. So what we are left with is a relation between psi dot and the Laplacian. So we find exactly the Schrödinger equation. So we find, and in fact we find minus plus here. IH bar psi 0 dot, if we write it that way, equals minus h bar squared divided by 2m Laplacian psi 0. Okay. So we find to this order, so up to order n equals 2, we find that our psi 0, our lowest order contribution, solves the Schrödinger equation exactly in the way we know it. So we have actually our psi here is, or in the non-relativistic psi here is this phase factor, times psi 0 that solves the Schrödinger equation. So this way, the Klein-Gordon solution and the Schrödinger equation solution are related. They are the same except for this phase factor in the non-relativistic limit. The only thing that is different here from the Schrödinger equation still is this prefactor minus plus, so there are actually two solutions of this S. And you can think of these if you remember that this time derivation here is basically just the energy or the Hamilton operator. So this is an expression for energy. So basically what we get are solutions of positive and of negative energy. And we now restrict ourselves to those of positive energy. This solves the usual Schrödinger equation. But this is, of course, an expression of the relativistic nature of this theory. So you know this also from the Dirac equation, for example. You get the positive and the negative energy solutions. So you get particles and antiparticles. And this is exactly the expression of that. So for every particle that solves the Schrödinger equation, there must be a corresponding antiparticle that solves the anti-Schrödinger equation, if you want. Okay, and now that we have this, we can also look at the next order. We can go to order n equals 3, and then we find a psi1 dot that depends on the second time derivative of the 0th order solution. But apart from that, satisfies the Schrödinger equation. So we can cast this into an equation. We can, and let me show this to you in the script. So we can now do the following. We can write this equation now at the order n equals 3. We can calculate psi 0 double dot from the 0th order Schrödinger equation. So this is just the Schrödinger equation applied twice. So it gives us a double Laplacian of psi 0. And then if we put all of those together, then we find the relativistic correction of the Schrödinger equation. So we can write the Schrödinger equation up to the first post non-relativistic order. So up to order 1 over c squared, we can write as IH bar psi dot dot equals minus h bar squared divided by 2m Laplacian of psi. And now we have minus h bar to the 4th divided by 8m cubed c squared. And then a double Laplacian. So this would be the relativistic correction of the Schrödinger equation. So we have this 1 over c squared term. And you actually see, so this is a momentum squared operator. So this is momentum to the 4th together with this h bar. So we get exactly what we found before from expanding the square root of the relativistic particle. We get a Hamiltonian that has a correction term minus p4 divided by 8m cubed c squared. Okay, and now, so now we have established the technique that we want to use. This is the method we want to use. So this way we could derive relativistic corrections to the Schrödinger equation. And you see we could now just go on and do this at higher orders. We could now do this at order n equals 4, always using the solutions we previously found. And in principle we could get relativistic corrections to any order in 1 over c squared. What you have to keep in mind is that we are basically just discussing a classical Klein-Gordon field here. So we are discussing a solution of the Klein-Gordon equation and how this is related to solutions of the Schrödinger equation. So there is no quantization here. So in this sense, we're discussing how the solutions of the classical Klein-Gordon equation are related to solutions of the Schrödinger equation, wave function solutions. So the quantization only comes from our interpretation of this. And we have to be careful because, as I've mentioned in previous lectures, these non-relativistic derivations are only appropriate as long as we assume that there is no mixing between sectors of different particle numbers. So basically what we assume is always that we can ignore particle creation and annihilation. And in this regard, this type of approximations seem to be good to get relativistic corrections to the Schrödinger equation. That's also why we are only interested in the lowest order corrections, because the higher orders would not tell us that much more information about what to look for, because then we also, when those become relevant, we also usually are in a regime where particle creation and annihilation becomes relevant. So now that we've established this method, let's see if we can do the same thing, but now for a Klein-Gordon field in curved space-time. So the first thing we need to do if we want to describe the whole situation in curved spacetime is that we want to rewrite our Klein-Gordon equation for the situation in a curved spacetime. And for this, we need to find the correct form for our D'Alembert operator box that enters the Klein-Gordon equation in a general curved spacetime. So we are now interested in what does the D'Alembert operator look like, and again expanded in orders of our epsilon, or 1 over c. What does the D'Alembert operator look like in a generic situation? And in order to get an expansion in powers of 1 over c, also for the D'Alembert operator, we make the following ansatz for our metric, or for the inverse metric rather. So this is kind of the crucial first step. So we expand our field phi as we just did before. We expand our field phi as a power series in 1 over c squared, or 1 over c in this case. But we also now expand the metric. We write the metric as the flat spacetime metric. Plus a sum over different terms, where k runs from 1 to infinity with powers of c to the minus k, and coefficients that we just call h mu nu k. So this is the general correction to the metric at an order c to the power minus k. Just briefly, so we are now expanding, you see, so before we expanded in powers of 1 over c squared, now we are expanding in powers of 1 over c. And the reason why we need to do this is that a generic metric can also have off-diagonal terms. So it can have time and space terms, and you know that the time variable always basically gives you a factor of c. So as long as you have a diagonal metric, you only get either c squared, because you have a tt component, or you get 1 from the space components. But now if we have a general metric, we can also have a mixing of space and time, and those will be of linear order in the speed of light. So this is why now we expand in terms of c rather than c squared. And once we have this metric, and now let me go to the script. So once you have this metric, what you can do is you calculate the Christoffel symbols in this metric, and you calculate the covariant derivative acting on a vector field, so the divergence of a vector field. And then with this you can rewrite the D'Alembert operator. So the D'Alembert operator in equation 1027. And you see that we split it in 3 terms. So we write our D'Alembertian here in 3 different terms, which are the following. So the first one is 1 divided by the square root of minus the determinant of the metric. So G without an index is the determinant of G mu nu. The derivative d mu of this square root of the determinant times G mu nu d nu phi. Sorry, this is the number operator acting on our field phi, I should say. The second term will be the following. It's d mu G mu nu d nu phi. And finally, the third term is simply the contraction G mu nu d nu phi. And now for the first and for the second, for the second and for the first, we can simply, so you see there is exactly our G mu nu enters here that we have defined as a power series, and we have in this case we have first order derivatives of our field, and in that case we have second order derivatives of this field. So again, as before, we need to calculate all the first and second order derivatives of our field in a general way. And we need to insert this power series expansion for our G mu nu. So while the calculation of the terms box 2 and box 3 are straightforward, for box 1 we need to do a bit of magic before we can write it in a proper way. So the first thing we do is we simply do an integration of the square root. So the integral of the derivative of the square root will be 1 divided by 2 times the square root, right? So here we will get 1 over square root minus g, and then this derivative is actually 1 over 2 times the square root. And then we have to take the inner derivative, which is minus the derivative of g. And G mu nu d nu phi. And now we do the following. We can now simplify it. So here G is the determinant. So now we can use the fact that in order to calculate the derivative of the determinant, that in general the derivative of a determinant of a matrix can be written as the determinant of the matrix times the trace of the inverse metric matrix times the derivative matrix A prime. So if we write this in the language of our in our covariant notation for G, then we would get the derivative d mu of G equals the determinant of G, so G times the trace. So we take the trace by multiplying with G alpha beta, with the inverse, and now the trace of the inverse matrix times the derivative. Sorry, so this is the inverse matrix matrix. This is a to the power of -1. And now we have d mu, g alpha beta, and we take the trace by having the same indices here and here. So we're summing with the sum convention over these indices. I think, okay, so appropriately, if you want to take the trace properly, then you have beta alpha here. So this is the transposed matrix. Actually, if you have this this product. Okay, so now now we can insert this here for our d mu g. And again, so here we just get minus g times 2. So this would just be 2g, and the minus here cancels. So we have just our d mu g here. So we have g alpha beta, d mu g alpha beta, g mu nu, d mu phi, and this derivative here is only acting on the alpha beta term. So this already. So now we got rid of the determinant here, but I need yet another color. What we have here now is instead of just having the metric g alpha beta, we also have the inverse metric here with the indices at the bottom. We can still rewrite this a bit so that we just get the inverse metric without the derivative. We can do the following trick. And sorry, I forgot to factor 1/2 here. So now we can rewrite this in the following way. So we let the derivative acting, instead of just acting on the g alpha beta here, we let the derivative acting on both of those. So let's write this as 1/2 g d mu g alpha beta g mu nu d mu phi. So this will just, by the product rule, this will give us this derivative, but it will give us the second one where the derivative acts on the first g alpha beta here. So we have to subtract this and get minus 1/2 g d mu g alpha beta g mu nu d nu phi. And now we observe that this is the inverse metric. This is the matrix. So this is just the matrix times its inverse. So this is the unity matrix. And of course, the derivative of the unity matrix is 0. So this term actually vanishes completely. And we have rewritten our box 1 expression in this way. And now let's inspect again what we have. So we find here again, as we had already in the term, as we had in our term box 2, we find derivatives of our inverse metric g alpha beta, for which we can just use the sum, for which we can just use the series expression here. And we have the inverse metric here. And now, sorry, I made a mistake here. The g of course cancels out here. So there is no g in all those terms. The g just the g just vanishes. The g just vanishes well, with this. So this g cancels the g from the square root here. Okay, so what we have is the inverse metric here, 2 times. But now we also find the metric g alpha beta. So our task is now, so we can directly use our series expansion for box 2 and box 3. But in order to calculate box 1, we need to find, in this expansion, we need to find now the inverse metric, the metric, sorry, g with the indices at the bottom. This is our next task. So in order to find the metric g mu nu, we write it in the following way. I've just already copied the result for you here. So we write g with indices mu nu as a matrix with indices mu nu. And now this matrix, this is our series approach for the inverse metric. And the inverse metric is the inverse Minkowski metric, eta to the power -1. So this you get if you multiply the unity matrix here with the matrix eta to the -1. And then we can write it as a series expansion. And so then we have our series term where we now write the h mu nu coefficients in matrix form. So as an inverse matrix, so the -1 here, as the inverse matrix of the matrix that goes with our h mu nu, times eta, and then times this eta to the -1, so it's actually the matrix H. And if we have this matrix form, then we can use the Neumann series for linear operators with the matrices, which is if we have an expression that is unity matrix. I don't understand why my camera blurs all the time. Okay, sorry for that. So we can write it as unity minus t for some matrix t. The inverse of this can be written as the following series expression. Can be written as the sum where n goes from 0 to infinity of t to the power n. Or if we just take the first order term out, so t to the power 0 is the unity matrix plus sum n equals 1 to infinity t to the power 1. So this is a general formula for bounded linear operators. So assuming that this inverse exists, then this is a converging series, and the other way around. So if the series converges, then the inverse exists, and we can calculate it this way. And we can now use this. To calculate our inverse matrix here. And this leads to the following result. So we insert this into our approach, and we get this expression. So we get eta, that's the one here, plus, and now we have the sum, n equals 1 to infinity. So you see we took the eta to the -1 out here of this Neumann series and just write its inverse directly as this eta. And then we have this sum over n that comes from the Neumann series, and and our terms Tn are actually this sum expression from our metric expression, or this sum to the power n. So this is our t to the power n. So our t itself now is a series. It's a sum where k goes from 1 to infinity. So we have a double sum here. So we have a product of two series, one with the index n, one with the index k. and we have these powers, nth powers of it. So how do we calculate those? And for this, you just need to use the Cauchy product formula for series. So in general, and I just give you the first one. So the expressions that you have are sum from k equals 1 to infinity. Then we have c to the power minus k. And then you have these matrices, hk to the power minus 1. Eta, the Minkowski matrix. And now we have the nth power of these expressions. So let's just look at the first one. Let's look at the square of this. And the Cauchy product for two series in general says that you now get a double sum. So you get k running from 1 to infinity, and you get a second sum with an index which we call I, which runs from 1 to k. And then you get the coefficients c to the power minus I, hi to the power minus 1, eta, so that's the coefficient in the series at value I, and you get the same but evaluated at k minus I. So this gives you c to the minus, so I minus k. H k minus I inverse times eta. And now we can just, so now you see we have minus I plus I here, so the I actually cancels. So this coefficient is just of the order c to the power minus k. So we get in fact this series with coefficients c to the power minus k, and then we have an expression here that is H inverse matrix I, eta, H inverse matrix k minus I, eta. So we have to be careful here because we're dealing with matrices, right? So the Cauchy formula you usually use for numbers, and it works fine, but it also works fine with matrices. You just have to be careful. You cannot simply commute those matrices, of course. So you have to make sure that you take into account that you don't change the order in which the matrices appear in this product, but this is not the case if you write it like that. So everything here stays in the same order. So now we have the square of this term, and now we can just iterate. Now we can do the same. Now we can use the Cauchy product again, multiplying this series with this series. And then we get another double sum expression, and so on. And this is done in the lecture notes. So you see here what you get if you take the third power, and so you can just iterate this. And for n, you get the following sum. You get a sum where k runs from 1 to infinity with coefficient c to the power minus k. So this is exactly the expansion in powers of 1 over c that we want. And then the coefficients you get at every order is a sum over j, so j1, j2 up to jn. Those are our additional indices that we need to sum over, where those j's all add up to the number k, and they all must be between 1 and k. And then you get this expression where you have an alternating product of an inverse of H with a certain index, the Minkowski matrix, inverse of H, Minkowski, and so on, n times. So with this iteration of the Cauchy product, then we get the final form of our metric, G near nu as a power series. We can now write the following way. So unsurprisingly, in that lowest order, it's just Minkowski. And then we get also a power series in K, so we get some K runs from 1 to infinity, C to the power minus K. And the coefficients that we now have look the following way. As a result, we get that they are another sum over another index n from 1 to infinity. It's an alternating series, minus 1 to the power n. And then we have an expression here that we call eta h tilde with two indices, k and n. H tilde minus 1 we call this. Eta mu mu. And this h tilde expression h tilde minus 1 kn is the following expression. It's the sum over these n indices j1 up to jn that sum up to k and are all between 1 and k. And then it can be calculated the following way: h to the minus 1 j1 eta h to the minus 1 j2 and so on, h to the jn minus 1. So once we have this, then we have to use the Cauchy product another time to calculate this g alpha beta d mu g alpha beta term that appears in our term box 1. And we can go through this calculation. So you do a lot of algebra in the end, and end up with an expression here in equation 1041. You end up with this final expression for this operator box 1. We can split it in the time derivatives and the space derivatives. So split it in the component t and the components I to ij that run from with indices that run from 1 to 3. And we have the final form of our operator box 1 in this equation 1042. And then we can go ahead and now find that we can write our D'Alembert operator in the following general fashion. We can write it as essentially being the Laplace operator at the lowest order plus the sum of terms at different order in C, which have a time derivative, first order time derivative. We have coefficients A for the first order derivative. Then we have AI, K, DI. So we have the first order spatial derivatives. And then we have the second order derivative, and I call those coefficients b. So we have bktt t squared plus bkti, so where I goes from 1 to 3, dt di, and finally bk ij di dj. So we get an expression in the end for our D'Alembert that has first order and second order derivatives in time and space with those 1 plus 3 plus 1 plus 3 plus and those are 9, but they are symmetric. So that's 3, 4, 5, 6 coefficients bk. And we can now use this expression for our operator box. And we have the concrete form of these coefficients a and b in terms of the metric. So I can show you this. So this is the general form that we had, and now we can write the a's and b's in this form from equations 1044 to 48. You find what these coefficients are and how they depend on our metric or inverse metric expansion terms h. And in particular, you can already calculate that a1, the time components, so t, tt, and the ti components at first order, so a1t, b1tt, and b1ti are all 0. So now, once we have the D'Alembert operator, then we can, as the next step, we can go ahead and insert it into our Klein-Gordon equation. So we do the same expansion of our field phi, with the only difference that we now also include odd powers of c, as I said, so we don't just have an expansion in powers of 1 over c squared, but we expand in powers of 1 over c. So the coefficient phi 1, for example, now belongs to the power 1 over c. So those are shifted a bit compared to what we found in the previous result. But again, we can insert those, and we can look at the Klein-Gordon equation at the lowest order. And at the lowest orders, we do not find any difference, unsurprisingly, to the case in flat space that we discussed before. So again, the lowest order, which would be the order c to the 4th, or remember before we multiplied the whole equation by c to the 4. So at this lowest order, we find again that the phase s is only a function of time. And then again, at the next higher order, we find that this phase s must in fact be plus or minus mt divided by h bar. So again, we get a positive and a negative frequency, positive negative energy solution with exactly the same phase factor in front. So again, we just choose the positive frequency solutions, and then we can, with this specific value for s, now we can calculate all the derivatives, all the first and second order derivatives of our field, dt, di, dt squared, dt di, and di dj. And for completeness, we also write the constant term. We write all of them where we pull out this global factor c to the 4th times the phase, and then we have the series expansions in powers of n. So having this, it's now straightforward to write down the Klein-Gordon equation. So all we have to do is use our equation that we found for the D'Alembertian on the left-hand side. So we go back to, so we use this form 1043 for the D'Alembertian on the one side, and we use these derivatives and we insert all of this into the Klein-Gordon equation, and what we end up is this lengthy expression here. In the first step, just inserted everything, and then in the second step, so you see we get a double sum still, we get a sum c to the power minus n, and we get a sum c to the power minus k. And we can just do a substitution here. We can do a substitution of n by n minus k. And then instead of getting this double sum with coefficients, we get a single sum with c to the power minus n, but with now the sum not running over, the sum is now not running just over n, but the sum is running over k and n, with the restriction that k must be smaller or equal n. So this is still a double sum, but we write it as as one expression with just a coefficient c to the power minus n. So we can contract those two coefficients so that we really can sort it by powers of 1 over c. If you look at this at the lowest order, at order n equals 1, which would be the next order that we haven't already considered, you just find that it will be trivially satisfied. So there is no new contributions at this order. So the first order we want to look at is the order n equals 2. And for n equals 2, we find the following expression. We find zero equals a constant, which doesn't really matter, 1 plus b2 tt plus 0. So, and this will also again be trivially satisfied, because we find that if we calculate b2 tt, we find that it is minus 1. So both orders n equals 1 and n equals 2 are just trivial. And then we can go, this is n equals 2. Then we can go to the next order, n equals 3. And there we find, actually, if we insert everything, we end up with h110 equals 0 as an equation. So we see that the order n equals 3 is actually not an equation for our field, so we still don't get a Schrödinger equation, but it's an equation that puts a constraint on our metric. Equation number 3 requires us that we can only have, so that the solution of our equation, that the metric we choose must be such, for our ansatz to work, there is a constraint on the metric. It must be such that the time component of the metric does not receive any contributions of the order 1 over c. So our time component can have orders of c to the power 0 and can have powers c to the minus 2 or lower, but it cannot have a contribution at the order h100. So this is a constraint on the metric that we get. And now at order n equals 4, we get the first time actually, for the first time we actually get something that gives us an equation for our field psi. And this is again the Schrödinger equation, but it's the Schrödinger equation with additional terms. So we get the following. So we get IH bar psi 0 dot. Then we get minus h bar squared divided by 2n Laplace operator. So up to there it's just the Schrödinger equation. But now we have additional terms. So what we have here is the following. So first, so we have this term m half h2 0 0, and if you then remember that the 0 0 component of the metric, or of the metric correction, is just the Newtonian gravitational potential, or rather 2 phi. So h2 0 0 is actually just 2 phi. If we again go to the linearized Einstein equations, what we did before, then this is exactly the Newtonian potential term. So this is just m phi. So we find at the lowest order, the non-relativistic order, we find exactly what we had before. We find the Newtonian gravitational potential here entering the Schrödinger equation. But we have an additional term here actually coming from second derivatives of the off-diagonal elements of our metric. So if our metric is not diagonal but has off-diagonal elements, then we get these additional terms. And now if we want to use this result, but we also want to look at higher order terms, that's what we are actually interested in, what are relativistic corrections, then it becomes quite tedious if you want to keep this general expression of the metric with the ages. So we want to now look at specific examples for a metric and then only work with those. And the first example that we can look at is the Post-Newtonian metric. So this is a form of the metric that goes up to order 1 over c squared terms. So if you only take the lowest order term, the lowest order terms, so you only take those terms, then you end up with exactly the Newtonian potential. So this is here, the Newtonian potential only enters in the time component. But now you go one order higher and you include correction terms that are also just expressions of this Newtonian potential. So it's kind of the correction to the Newtonian potential at relativistic order. And we can do this, and we can calculate the different expressions that we need. We can calculate all the coefficients a and b that we need for this specific metric. And then we get the Schrödinger equation with the Newtonian potential at the lowest, at the order n equals 4 that we had before. And now we can go one order higher, and again we get a Schrödinger equation for our psi1, so for the first order correction of our field. And we can go another order higher where we get additional conditions for our coefficients. And now we can insert all of those or we can look at the Schrödinger equation for all of those, and again use the lower order Schrödinger equation to make replacements. And then basically at the order psi2, so at the quadratic order, we end up with a Schrödinger equation that we can express in terms of a Hamiltonian, which looks the following way. So this post-Newtonian Hamiltonian is first the non-relativistic one, that's just the standard Hamiltonian. P squared divided by 2m plus m phi. And then we have the relativistic correction. So plus 1 over c squared. And we have minus p to the 4th divided by 8m cubed. Do you recognize this? This is what we also had without the gravitational potential. So this is just the special relativistic corrections. And now we have the gravitational correction terms. So we get the term minus ih bar divided by m. Gradient of the gravitational potential times momentum. Minus gravitational potential times kinetic energy plus m half phi squared. So this is the Hamiltonian of a Klein-Gordon field in the post-Newtonian metric. And the next thing we can now look at is the question, well, if we are in a lab on Earth, we are interested in the situation where we do an experiment on Earth and we are interested in the effect of the Earth's gravitational field, then we can, so our Earth is just a spherical symmetric. In first approximation we ignore its rotation, and so it's just a spherical symmetric solution. It's a Schwarzschild solution of the Einstein equations. So we can in principle use the Schwarzschild metric that describes this, but you have to always say which type of observer you are looking at. And you can look at a so-called shell observer. So an observer that is just hovering at a constant distance, r, from your potential, from your mass. So we have some mass m here, and it actually turns out. So if you have such a shell observer, and you have the Schwarzschild coordinates, such a shell observer measures time so his proper time is actually an expression that is the square root 1 minus 2m divided by r dt. So you see that for such a shell observer, the proper time observed by this, so what the shell observer reads on his clock, is not the same as the time coordinate in the Schwarzschild metric. It only becomes the same if this radius goes to infinity. So the Schwarzschild coordinates basically describe the space-time of the spherical space-time from the perspective of a far-away observer, so an observer that's a very large distance. So this is not what we have on Earth. So in this sense, the Schwarzschild metric, although of course the Schwarzschild space-time describes the space-time of our Earth, the Schwarzschild metric is not, the Schwarzschild coordinates are not good coordinates to describe experiments on Earth. What we can, however, do is we can take into account that where we are on Earth, close to the center of the Earth, we find an approximately homogeneous gravitational potential, and such a spacetime is properly described by Rindler coordinates. You can, in a more rigorous way, whenever you have an observer on a geodesic, then you can use so-called Fermi normal coordinates. So that's a general set of coordinates that's co-moving with an observer. And those you could expand, and as long as you're locally, as long as you're close to this observer, at the first order, you would describe those by this Rindler spacetime. So then the metric we have the following: the Rindler metric just gets a contribution in the time component. So it is just minus 1 plus phi divided by c squared. So it's up to 4 order 1 over c to the power 4 in the time coordinate. But the spatial ones are just Minkowski. So we have plus dx squared plus dy squared plus dz squared. And in this you can calculate, so first of all we find again that our H200 component is 2 phi. We can also calculate H400, which is minus 3 phi squared. And now, so again, we have the constraint that our h1, 0I, or we have, sorry, we have an, yeah, h1, 0 is 0, that's satisfied, that's the constraint. But we have the additional one, so we have h1, 0I, so those are 0, those we would need. And now we can calculate, let me just switch the screen. So now with those we can again calculate these trace terms that we need in order to derive our coefficients a and b, and we can get all the coefficients, and again we find a Hamiltonian for this. And the Hamiltonian in this case, the Hamiltonian that goes with the Windler metric is the following. So again, it's exactly the same at a non-relativistic order. Plus 1 over c squared. And again, we find the special relativistic correction term, p4 divided by 8m cubed. We also find the minus IH bar times the gradient of the potential times p term, just as before, and we find phi coupling to the kinetic energy, p squared divided by 2m. What we don't have, in contrast to the Post-Newtonian metric, is the phi squared term here. So in the Windler coordinates, this is the Hamiltonian that we need. And now, sorry. Oh yeah, sorry. The one thing I wanted to point out. So it also differs by the sign of this coupling term. So this was a minus in the PPN in the Post-Newtonian metric, and now we have a plus sign here. So this one changes sign, and we don't have the phi squared term. And this is now the metric that the Hamiltonian that we want to consider. So we found a Hamiltonian now that up to order 1 over c squared describes a Klein-Gordon field in the gravitational potential of the Earth. It's not super surprising. Most of the times we found before already with our other approaches that we used, like expanding the relativist point particle or from the phase shift. But the point is that now we have a rigorous derivation where we really looked at the solution of the Klein-Gordon equation in a curved space-time. And we get this Hamiltonian, but it's a Hamiltonian for a classical Klein-Gordon field. So the interesting question now that we were faced with last time when we talked about the superposition of clocks is, if we have something like this, how can we get an equation for a system that is constituted of many particles, and how can we draw conclusions on the motion of the center of mass of such a system? And this is the next chapter. So now we want to find relativistic center of mass variables, and this is actually not a trivial question, or it's actually one that cannot be solved at all, in the sense that a relativistic center of mass, as we have it in non-relativistic mechanics, does not exist. So the center of mass in non-relativistic mechanics has two important properties, namely that the center of mass variable with the total momentum forms a canonical pair, so they are canonical conjugate variables, and the center of mass itself moves like Galilei invariant object. So if you transform from one frame to another frame, the motion of the center of mass, so it doesn't matter if you calculate the motion of the center of mass and transform it to another frame, or if you go to another frame with the particle coordinates and calculate the center of mass in this frame, you always will end up with the same center of mass. And it turns out that in relativistic physics, those two properties are incompatible. So we have to make a choice. Either we keep the canonical commutation relations, but then we end up with a frame-dependent definition of center of mass, where when we Lorentz transform to another frame, the center of mass calculated in this frame will be different from the center of mass from the other frame transformed into this frame. Or the second choice would be we have the Lorentz invariant version of a center of mass, but we lose the commutation relations. Now, the commutation relations in quantum mechanics are of course quite important. There are a lot of fundamental properties of quantum mechanics rely on these canonical commutation relations between momentum and position. So the choice that we make now, but it's really just a choice, is that we are trying to define center of mass variables that still have these canonical commutation relations. So we need to keep in mind that everything we're doing now gives us a center of mass only in one specific frame, and we have to be careful if we are Lorentz transforming between different reference frames. What we do now first is that we have a look at the Poincaré group, which is the symmetry group in relativistic mechanics. The Poincaré group has 10 generators, so it has the generators P for translation, it's on a vector. It has J for rotation, those are also 3. It has 3 boost generators, which we call K. And then it has the time translation generator, which is usually called H, because it is, of course, related to the Hamiltonian, to energy. And those satisfy Lie algebra. Namely, I just skipped the commuting ones. So the PI's commute with, the P's commute with each other, and they commute with H. And also the J's commute with H. The J's will satisfy the algebra J. Commutator equals I epsilon I j k jk. And you get similar expressions, which you can find in 1080 for J with P and J with K. Also we have Ki with the time translation generator is I times Pi. And now the most crucial ones for what we want to do here is KIP per Pj. Those are 0 if I and j are different, but if they're the same, then we get I times h divided by c squared. And the commutator of Ki with Kj is minus I epsilon ijk jk divided by c squared. Now we can do the following. We can look at the representation of those generators if we have spinless particles, and then we can just we can just write P as the total momentum, so it's the sum of all the particle momentums, which we call P mu with indices mu. The same way J would just be the total angular momentum, so this is just the sum of the particle angular momentum. And H we can actually write as the sum of all the kinetic energies of all particles plus U, which is the potential that contains all the interactions between particles. And then finally we find a form for K, which I do not give here, but you find it in the lecture notes. So K will also depend on the kinetic energies. And K contains another potential called V, which is called the interaction boost, which we need for relativistic covariance. But this is not the most important thing to understand here. So the important thing to understand is that the kinetic energy here, the particle kinetic energy T mu, in a relativistic context can be expressed, of course, by the relativistic energy condition. So this is P mu squared C squared plus the mass of the mu particle squared C to the power 4. So, and in this sense, we can write for n particles in a relativistic case, we can write these generators. Now, in the non-relativistic limit, we can simply take C to infinity, and then we see that this energy T mu gives us an mc squared at the lowest order. So this mc squared via h enters here and cancels the c squared. So in the non-relativistic case, we get a mass here as the commutator, and this commutator will just be 0. And this algebra that we get then is called the Bargmann algebra. So it's the central extension of the Galilei group algebra, where the total mass m, so m here is the total mass of all the particles, so the sum over the sum of all the mu's. So this total mass acts as the so-called central element in this group. So the crucial thing is that we then find, and instead of showing that at the board, I just show you the equation in the lecture notes. So what we find then is that the generators take in the Galilean case, and in the non-relativistic case, take a so-called single particle form. So they look exactly like what we would get just for a single particle, just now with the total momentum and the center of mass position. So if we introduce Galilean center of mass coordinates, then those bring those generators to a form that looks like a single particle, with the only difference that here our Hamiltonian or our H generator gets an additional small h, which is the internal energy. And now what we are doing now is that we require for our relativistic center of mass variables, we require exactly this property also in the relativistic case. So we require that we find coordinates r and p, and relative coordinates for p is still the total momentum, but we find the coordinate r such that in those coordinates the relativistic generators, or the relativistic generators of the Poincare group take a single particle form. So in particular, this means that our H generator is supposed to be the total momentum squared c squared plus the internal energy squared. They remember that this this h squared must now also contain the rest mass energy, so the m squared c to the fourth term. And this we can do, and then it's rather complicated, but it can be done to actually find a concrete representation, or to find the concrete coordinates in which this form exists. There is a quite complicated paper by Foley and Krajcik from the 1960s, and they do this in a perturbative way, but it already looks very complicated at the lowest orders. But this is not our concern here. The main result that we get is that now in this definition, in this precise definition, the Hamiltonian we get, at least in Minkowski space, so the Minkowski space Hamiltonian for those specific variables, you can just see here, is exactly this expression. So we get the square root p squared c squared with the center of mass momentum plus the internal energy, as we would have expected. Naively, we can write this as our Minkowski space Hamiltonian, but we need to keep in mind what this is. So this expression gives us exactly the center of mass coordinates in which the Poincaré group generators take a single particle form. And now we want to generalize this. Now we want to generalize this to the case we are interested in, namely to the Rindler space and to Rindler coordinates. And you can really only so everything that happens between equation 1088 here and the result 1092. You can just skip if you're not very familiar with general relativity. So this is quite technical, and it's really not the crucial information here. So what happens is that we can argue that in Rindler space the Hamiltonian must then be just the Minkowski space Hamiltonian plus this anticommutator of position and Minkowski space Hamiltonian times g divided by 2c squared, where g is the acceleration in this metric. And now we can expand the internal Hamiltonian in powers of 1 over c squared, and we end up with center of mass Hamiltonian now, so in Rindler space. We end up with the following Hamiltonian. We get the total mass times c squared, that's just the rest mass energy. We get a center of mass term, p squared divided by 2m. This is the center of mass kinetic energy. We get the internal energy at lowest order, and we get the gravitational potential, m times g times the center of mass position x. So really at the non-relativistic level, nothing exciting happens here. This is just what we expect for a particle, that its center of mass behaves like a single particle. And now we look at the relativistic corrections, and again we find the kinetic energy, the relativistic correction to the kinetic energy, which is minus p4 divided by 8n cubed. We find the internal energy at first relativistic order. We find a term that's minus p squared divided by 2m squared times 8,0. So this is actually what we formerly attributed to relativistic time dilation. So it's a term that couples the kinetic energy of the center of mass to the internal energy. Then we find a term that we didn't previously find, which is an anticommutator of x and p squared. And we find the term that we attributed to relativistic time dilation, so a coupling of the internal Hamiltonian and the center of mass position. So we find basically the terms we worked with before, and for the superposition of clocks, we had this gamma that was basically those two terms. But you see there is an additional term, so we need to really be careful what we are doing. So this additional term has not any consequences on what we discussed before. So all of this was correct and all of this stays correct. But you see, if you do things rigorously, there are additional terms that you don't get in this naive treatment where you just replace the mass by mass plus h divided by c squared. So with this brief rundown of how you do these things rigorously, I hope I didn't overwhelm you. I understand that this was a lot, but I wanted to give it to you in a thorough picture. Again, don't be scared if you didn't understand every single detail of the derivation. We will also have time to discuss all of those steps in the Zoom meeting. And again, please, as an assignment, go through the lecture notes and make sure you understand the crucial points and the crucial arguments in this. Next week we will do something similar, but next week we will for the first time discuss the effect, how does the quantum system gravitate, so how does quantum matter act as a source of the gravitational field. Thank you for listening and see you next week.